down south of it. So my research question is, how can we quantify probable maximum fire weather risk to the electric grid in British Columbia? I have three objectives for meeting this question. The first is to investigate fire regimes of British Columbia using the most recent wildfire occurrence data with reference to electric grid infrastructure. Secondly, to identify the best fire weather metrics to use for a risk map and for future climate projection. And finally, to define a probable maximum risk index based on past wildfire behavior, fire weather indices, and incident data from BC Hydro. And I know in this space, we talk a lot about sort of public safety power shutoffs, and probably many of you are familiar with weather forecasting models that determine risk of ignition. But the perspective that I'm looking at this is more in terms of long-term forecasting for future climate to help with grid hardening efforts in the future. So in looking for a model to achieve this goal, I've come across a number of probability of fire occurrence models. So there are several model frameworks that have been developed to give the probability of wildfire occurring in a certain region based on weather, fuels, topography, population data, etc. And these models can range from simple stepwise linear regression to more complex machine learning techniques such as random forest classifiers, gradient boosting, and UNets. The plot on the right comes from this paper in 2014 by Barbero, and they separate out different ecoregions of the United States and train them based on a simple stepwise regression. And then they give a probability of fire occurrence based on each ecoregion, and then see how that probability changes over time. And so this was sort of an inspiration for me to apply this to my own model and look at this from the perspective of climate projections. So rather than ecoregions, which was used in the Barbero paper, I choose to use the fire regime types that were developed by Sandy and Ree in 2019 for Canada. The fire regime types provide a broad perspective of regional fire behavior by considering the geographic distribution of wildfire characteristics. So the four wildfire characteristics that they use to determine their different regimes are the fire size, fire frequency, the seasonality, and the ignition cause. And then they also did some more extensive analysis of local vegetation, topography, and input from fire experts to determine the exact boundaries. So just as an example of one of these regime types here, let's look at regime type 2. So FA2 represents the fire activity based on the fire size and frequency. SESU means that this region sees primarily summer fires. And then ICLT means that the ignition causes in this region are primarily lightning-caused ignitions. And so here is a breakdown of the different characteristics that inform those regime types. You can see for all of Canada, the seasonality, whether we have spring, summer, or a mixed fire season, the ignition cause, fire sizes in different bins of hectares, and then the frequency and burn rate per year. So before applying these regimes to my model, I first wanted to sort of verify that they still hold, because the regime types were developed based on data from 1970 to 2016. So I looked at the last decade of data, and I plotted just sort of a qualitative validation analysis looking at the seasonality and the ignition cause. And for these two in particular, there's very little change from what the Enry paper found. You can see that they're sort of correlated, where we see a lot of human-caused fires in the springtime, particularly in this sort of Peace River region up here, and then also a bit in the Okanagan. And then a lot of our summer fires are non-human or lightning-caused fires. Then I looked at the fire frequency for the last year, and these grid cells are based on the ERA 5 grid sizes, which is what I'm using for my model. And the Enry paper uses it in megahectare, so I just looked at the fire count for the whole decade. And you can see that Southeast BC has the highest frequency of fire occurrence in sort of this central southern area as well. and fire frequency is relatively low along the main north-south transmission line in the middle of the province, so hopefully that still holds in the future. And the general sort of pattern of low fire frequency along the coast matches with what we see in the ENRI paper. And finally, I looked at the fire size, and this was the one that showed a notable difference between what the ENRI paper found. So we see a notable increase in fire sizes throughout BC in the last decade. All of the darkest green dots on the left represent fires that are greater than 1,600 hectares in size. And this holds all throughout BC, where we're seeing an increase in fire sizes compared to in the ENRI paper. But this particular aspect of the fire regime types may be negligible for our purposes because we are interested in fire occurrence regardless of the final fire size. So after my initial validation of the fire regime types, I regridded all of these regime types for my model to match the ERA 5 grid. You can see all the regime types on the left, and each separate regime will be separately trained on ignitions data from the CWFIS, which are the red dots. So for my previous analysis that I showed, I only included fires greater than 50 hectares in size, because that's what's outlined in the ENRI paper. But for my model, I decided to include all fires, including the smaller fires. And I'll go into that a little bit more into detail later as to why. So for the weather variables that are going to be driving my model, I'm using the fire weather index and all of its components. So for those of you who are unfamiliar, the fire weather index is the most globally used index of its kind for predicting fire weather. And then it is composed of 3 different fuel moisture codes that represent different timescales of weather. All of them are initialized off of new local weather variables of temperature, relative humidity, wind, and rain. And they're calculated iteratively, and so that's why the previous day's fuel moisture code impacts the next one, and that's why they represent sort of different timescales. So the fine fuel moisture code is representative of the past few days of weather, the DEF moisture code generally around the past 2 weeks, and the drought code is long-term drought conditions, particularly over the last 2 months. Then the initial spread index, which is a combination of the fine fuel moisture code and the wind value, is the expected rate of spread. And the buildup index represents the total fuel available for combustion. And all of them sort of combined are the fire weather index. So here's an example of one of the components, the FFMC. So I calculated all of these components for each day from ERA 5 input for 2018 to 2024. And this is the time period that corresponds with the outage data that was provided to me by BC Hydro that I'll be using to sort of make a risk analysis of outages. So I chose one regime to start with to test, and this is regime 13 shown in the right. This is its fun little code that's associated with it, and this means that it has low to moderate fire activity, summer season fires, and it's a mixed ignition regime, so it has both human and lightning caused ignitions. And so the idea is that for just this regime, and for each unique regime type separately, I calculate each grid cell's daily maximum wind speed, minimum relative humidity, maximum temperature, and then all of the FWI components that I outlined previously, which are based on new local time. I do some sort of stepwise regression to train all of the inputs on the grid cells with and without fire occurrence, and I get some equation for probability of fire occurrence, in this case, of the most important weather variables driving the potential of ignition and their respective weights. And the reason why I chose to start with a stepwise regression was to sort of tease out these most important variables so that I can verify that, my machine learning model is correctly choosing the most important ones. Some other training considerations. I mentioned earlier that I chose to include all of the fires in the CWFIS dataset, not just the ones greater than 50 hectares in size, because it makes my dataset about 20 times larger. And I also think it's important to capture all of these ignitions when we're talking about risk to the grid and not just large fires, because depending on where the ignitions occur, they can be very disruptive in their own way. And I'm currently training only on the fire season data for regime 13. As I mentioned earlier, this is the summer months of June, July, and August. So you can see in this time series that um, um, with both just the fires above a certain threshold and all of the fires, we have the summer seasonality. Um, so yes, I'm training just on the summer for now. So for my stepwise logistic regression model, I isolated the summer months. I used a standard scalar or z-score standardization. I used recursive feature elimination to remove the less important features, and I get this final probability equation, which includes the maximum temperature, the dust moisture code, the drought code, and the buildup index as the most important variables driving fire probability for regime 13. So all of that was trained on the data from 2018 to 2023. And then I applied the derived equation of probability to weather data for 2024 for the entire fire season and compare that with the actual reported ignitions that happened in 2024. So the actual ignitions are the black dots. And then, the grid cells are my predicted fire probability. And this is my ROC curve, which shows the false positive versus the true positive rate for, excuse me, for the stepwise. And I have an area under the curve of 0.70. An area under the curve of 1 represents a perfect model, and 0.5 is completely random. So it does okay. And I think that one thing that's quite interesting is that for this sort of southern portion of the regime, it does pretty well where the lower probabilities don't actually have a lot of fires, but it doesn't do so well in these northern bits. So that's something I'll probably have to look into if maybe I need to reassess how I'm regridding the fire regimes. So those are my results for the stepwise regression, but my ultimate plan is to use a machine learning method, and for that, I chose extreme gradient boosting. These methods have been applied to similar models for forecasting wildfire currents using a variety of input variables that influence fire behavior. And XGBoost works by creating an ensemble of decision trees, and then it iteratively adds new trees to correct the errors of the previous ones. It incorporates L1 and L2 regularization to prevent overfitting, and so far, I'm just using the XGB classifier, which is a simpler application of XGBoost that is compatible with scikit-learn pipelines. And I have a little less control over the training process, but it's useful for me to try to figure out how best to, what variables are most important for this model for now. So this is my initial test with the XGB classifier with just a standard scalar and hyperparameters and applying weights based on the class imbalance ratio. So the no fire days over the fire days to give some weights to my probabilities. And actually it does worse than the stepwise model with an AUC of 0.66. And part of the reason for that is it gives some higher fire probabilities in some of these areas that don't really actually have a lot of fire happening as compared to my stepwise model. And that might be because of the influence of the other weather variables that were included. So I have the SHAP values for the XGB classifier. So SHAP values for each feature represent how much the feature increased the likelihood of fire occurrence. A positive SHAP model means that it increased the likelihood, and a negative one means that it decreased the likelihood of fire. And then the actual values of each feature are shown by the color bar. So for example, the pink buildup index values are high buildup index values, and high buildup index values have a positive shot value, which increases the probability of fire occurrence. But one thing that you'll note is that it identifies the same main four drivers of fire occurrence as the stepwise model, that is the buildup index, the maximum temperature, the DMC, and the DC. And what's sort of interesting is that these other variables have a sort of indistinguishable effect, but also it seems as if high initial spread index, for example, gives less likelihood of fire, and that is the case for all of these variables, which should be associated with a higher fire probability. So there's something going on sort of fishy there that I'll have to dig into a little bit further. So that's where I'm at with the XG boost. I just wanted to look firstly at the weather variables, but I plan to include other data sets to improve the predictability of my model. So I have this outage data that was provided me by BC Hydro, and eventually I'd like to use that as a target output to also give some probability of outage associated with certain weather patterns. And then I'd like to include a fuels data set to see what the impact of different vegetations are on this model. And eventually, I'd also like to include a population density data set to evaluate the actual risk associated with a potential outage. And there's a 10-kilometer gridded data set available from Statistics Canada that I will end up implementing. And then for the climate data, so once I've finalized my machine learning model, the ultimate goal is to project for future climate where these probabilities, how they will change in the future. So I'll be using the NASA NextGDP statistically downscaled CMIP6 data set, which was brought to my attention by some folks in the Wired group. It has data daily from 1950 to 2100. It has the same spatial resolution as the ERA5 data, which is nice. I don't have to take that into consideration. And then it includes the historical scenarios, and then the SSP 245 and 585, which are the middle of the road and like worst case scenario climate scenarios. It's a really great data set because it has over 30 models available. So my next step would be to choose models that represent sort of a different range of known warm or cold biases, then bias correct each of them relative to the ERA5 data set that I'm working with, and create an ensemble for climate projection. So in conclusion, I have completed a verification of fire regime types, which revealed changes in fire size, but not in the geographic distribution of other wildfire behavior characteristics. So I'll go ahead and use that for my model. And I've done an initial stepwise logistic and XGBoost model framework based on these fire regime types, and found that this regime 13 representing central southern BC, its ignition likelihood is driven by maximum temperature and FWI components that represent longer-term weather patterns. And my future work is that I'll finalize this machine learning model framework and hopefully improve upon it and apply it to all of the different fire regime types separately, and include the additional data sets that I outlined to determine risk of outage, and finally apply climate projections to the machine learning model to evaluate future risk. So here are my citations, and I'll take any questions.
Thank you so much, Mina. I think Mohsen has a question, and other attendees, you're welcome to ask any question if you have.
Okay.
Thank you, Mina, for the presentation. Can you go back to slide number 14?
Sure.
I think there is a lot of work that share with what I'm doing. We should talk offline, but this number, I mean, I've started working with FWI. The problem I have is that like is this FWI is designed for forest, so not for urban areas, right? My question is that how do you take it to be usable for urban areas? That's my first question. And also, FWI has temperature inside, but on top, the top box also has temperature. It's like taking temperature twice to me.
Sure. So I'll go ahead and address your second question first before I get to the first one. So the FWI is calculated based on the noon local weather,
Correct.
and
Correct.
noon doesn't necessarily represent the daily maximum temperature. So that was sort of my reasoning for including both the daily maximum and minimum values of this and also the FWI. But yeah, maybe I should confirm how different they might be from the noon local weather. Yeah.
Okay.
As for your question about the urban areas, this isn't necessarily something I've taken into consideration. I think the data set that I'm working with is quite coarse, so I'm not sure how much of my grid cells would be entirely urban. And I think especially for when I'm looking at risk, particularly to the transmission lines in BC, they're in rather rural forested areas. So yeah, I guess that's sort of my
I
justification
see.
for using FWI.
Because I mean, the source of fire is mostly forests and trees rather than urban cities. So one challenge could be like where it happens, because this is the possibility in trees, not in cities, right? So where it happens and how long the fire happens to the cities, and what's the wind direction. These are like kind of challenges, at least for me. And if you go to slide number 16, I have another question there. So and 17. So this is a really interesting function to me. So I maybe we can talk like separately how you came up with this function, because this is really interesting to me to see maybe using in my research. And if you go to the next one, I have another question here.
Okay.
What you say is like it's not working very well on the north, but on the south. So probably not, because what you're doing is a probability between 0 and 1, right? But what the black dots are is on and off. So they're not taking the possibility, they're saying yes or no, right? Is it happening or not happening? So I'm saying like your model is working very well, because what you do is just like it is possible and it happens, right? On the north. I'm not sure how you can convert that black dot dates data to make it something like what you're doing, a possibility between 0 and 1, not only 0 and 1, like a range of 0 to 1. That was my question, if you have any plan for it.
Yeah, I don't have a plan to turn sort of the actual ignitions into a probability. I'm not entirely sure of a good way to do so. That's sort of why I ended up using the ROC curve to test sort of how well the model is doing. Because yeah, it's pretty hard to assess like how well the probability in just the plot is doing
If
compared to
if you
each.
have if you have any data about the severity of these fires, that could do the job for you. I'm not sure if you have that data, because what I'm saying, like your model is working very well to me, because you have predicted a possibility and it happened, but it doesn't say how severe it was, right? That could kind of like convert that 0 and 1 dots to a range of possibility between 0 and 1. Just a
Yeah,
suggestion if you have that data.
I don't think I have some severity, but I do have like fire sizes. So
Uh-huh.
that could be
Could be.
a way to assess the severity of the fire. But I think I'm sort of interested in just any sort of ignition that occurs, because sort of the long-term goal is to see areas where in the future we might see increases in fire probability. Because I think yeah, like the ultimate goal is for long-term planning of grid hardening. So if once I do my climate projections, I see in this particular region we're going to see a huge increase in the probability of fire, then maybe that's somewhere where utilities might want to target their grid hardening efforts, or maybe they might not want to expand into these areas or something like that. Yeah.
Okay, thank you so much. I'm not going to take everybody's time. We can talk later. Thank you.
Yeah, that sounds great. Thank you.
Yeah, thank you, Mina. I think Ladan has a question. Please go ahead.
Yes, thank you. Thank you, Mina. It was a great presentation. It's also very relevant to my research line. I also work on fire. And I have kind of similar question, but I think about the probability estimation based on the binary data. I think that the logistic regression will actually do that, because if you have only two classes, just to comment on what Mohsen said, is that when you have a binary, like a binary problem classification, the sigma function in the training process actually output a probability, and then you set a threshold based on whether you want to split it to 0 or 1. If you just set a threshold based on like 50% probability, but actually you are training to get the probability, but at the end you just convert it to a binary to match the class. So I think if like what you have here can also like predict the probability, even though we don't have the probability as the input for training.
Okay.
But if you go to slide 14, this one, so you have two types of data, like you have the maximum daily maximum wind speed and relative, and also the FWI component?
Yeah.
Oh, okay. Because I think that, for example, on like the equation that you use for the probability, I think ISI internally.
Oh, sorry. Yeah.
Yeah, the same page. And ISI internally has the FFMC and window speed encoded. So you kind of like, I think you're just using it like the same variable twice, I guess.
Yeah,
Like,
I think so.
yeah.
This was something also that Mohsen brought up, and my justification for doing so was that the maximum values might not necessarily occur at noon local, but perhaps I could do like a plot of, comparing the noon local values and also the maximum ones to justify separating them out, because if they're not that different, then you're right, I'm basically including them twice. But if they are different, then I think that would be justification for including both.
Yeah, that's a good point. And also like you're estimating the probability of having a fire ignited at a specific cell, right?
Yes. Yeah.
Mm. And I was like, I think like maybe wind speed is highly relevant, but I think from the SHAP value you realize that it wasn't that relevant, or it was like mixed comments on that?
Yes, but for this particular regime. So it'd be
Oh, okay.
interesting to see, like, my idea was that all of the different regimes would be driven by different fire behavior. So perhaps there are some regimes where wind speed is really important. They have a lot of wind-driven fires. So this is something that might require further analysis. I still think, yeah.
Okay, I see. But I'm just curious about like actually from like a fire science perspective, does wind actually affect the ignitions? Like if you have like.
It's a good question. I don't know. I would
All right,
assume like if it's very windy, but yeah, we often think of the wind in terms of like fire spread, but
Yeah.
I feel like wind could affect ignitions if, like for example, maybe like there's a lofted ember, and then if there's already fire nearby, then in a very windy regime, you might get more ignitions that occur as a result of that. Maybe I would be capturing those fires, but yeah.
Maybe like for the spotting could be like a relevant factor for the spotting, but yeah. Thank you. It was a great,
Yeah.
I think we need to talk a little bit more outside. So thank you.
Yeah, sorry, one more thing about the wind is like, so I know that a lot of sort of human-caused fires in California, at least, especially like the grid-caused fires, are associated with heavy wind events like the Santa Ana winds. So a lot of the times it's like things blowing into the lines. So I think it could be that winds do cause ignitions, especially in more urban areas. So it'd be interesting to see one of the different regimes that represents a more urban area if that's something that pops up. But yeah, thanks, Ladan.
Yeah, interesting. Thank you.
Thank you, Mina. I think Dr. Kevin has a question. Please go ahead, Dr. Kevin.
Yeah, thank you very much, Mina. I really enjoyed your presentation. It's wonderful to see the work that you're doing and where you are in it. And I'm just going to follow up on a couple of themes that my colleagues brought up. I think you're right about wind and ignition. It's an interesting relationship, but it could be something like the spread of embers. We've certainly seen that in the Okanagan and the catastrophic outcome from that. Maybe enhancing the conditions that could cause wildfire to spread or make it easier for other ignition sources to be successful, intensifying heat conditions. So it's kind of it's a kind of an indirect relationship, but I think you're quite right. It is there. My question, and it comes down to, you mentioned probability. I think that was also mentioned by one of my other colleagues on the call and so forth. And I'm really interested in how what you're generating can be used and where you envision it being used in the kind of in an applied way. And you mentioned maybe siting or routing decisions. And in that vein, I'm thinking, would it also contribute maybe to our thinking about the investment of resources and sort of armoring or hardening parts of the grid and so forth? How and would it fit into, your outputs would then fit into another kind of a risk analysis or risk management frame? It would be part of one of the building blocks of that kind of a system.
Yes, that's it. Exactly sort of the ultimate goal. So right now I'm just sort of giving these probabilities of fire occurrence, but then I also have some outage data and I might include some population data. So I come up with some sort of framework to give, that risk based on like, where we have a lot of population and where we might have previously seen a lot of outages. And in combination with the fire probability, that might outline certain grid cells where utility might want to focus their grid hardening efforts, especially along the distribution line.
Mm-hmm.
And yeah, and with the future climate projections, let's say we see a huge increase in fire probability, that might also be a consideration for them, especially if we need to do some grid hardening on like major transmission line or something that they can start planning well in advance. That's sort of the idea.
Yeah. Yeah, I can see that, and I'm thinking like the two sides of a risk analysis and where it would fit in, and you're doing a little bit of work on both sides of that dimension, thinking about the kind of the outcomes of some kind of top event. And I think one of your maps showed Southern Ontario. Is that correct? Did I see that right?
For right now, I'm just looking at BC,
Oh,
but
okay.
some
So
of
I
the
missed.
data sets are just all, I think it's maybe this one. This is just a
Yeah, that was it.
example. Sorry, it's
Okay,
probably
okay, okay.
confusing. This is an example of the population data set that I intend to use in the future, and I just pulled this
Right.
off of their website.
So, and I apologize, my mistake on that. So, I think what I find fascinating about that is that we do think a lot about the transmission system, but then there's the enormous and complicated retail distribution system too. And we see the risk that wildfire poses to some of those subsystems too. So I think, yeah, it'll be interesting to see how your work evolves and maybe the applicability to that field as well, which, seems a little bit under-tilled at this point. Thanks
Yeah,
very much.
yeah. Thank you.
Thank you so much, Mina, for the great presentation. If there is not any question, we can conclude the meeting just right now. Yeah, it seems that there is not any questions. Thank you so much, everyone, and thank you, Mina. Have a great one. And just as a quick note, I think we have our Wire and Wednesday seminar on September 24th. And Dr. Nicholas Coops and his team are going to do a presentation. We are looking forward to this presentation. And we are looking forward to seeing you all. Thank you so much.
Thank you.
Thank you.